Hi, welcome to Lecture 6 of the online course on Explainable Machine Learning and Artificial Intelligence. This will be the first lecture in a series of 2 on a class of methods for generating explanations called Model-Agnostic Post-Hoc Explanation Methods. The global goals of this lecture and the next one will be to recall what are post-hoc methods for explainability, define the class of model-agnostic methods and discuss their importance. Then the main part of these 2 lectures will be to review some of the most common methods of this type. We will start in this lecture and continue in the next one. Altogether, we will seek to relate the different methods to each other. Before we dive into this new class of methods, let me take a step back and remind you of what we're trying to achieve. The goal of explainable machine learning is to develop models that provide explanations to the human users for the decisions that they produce. The key question is how to generate explanations from a machine learning model. Going back to the machine learning pipeline, I told you that one approach for generating explanations is to use models that are inherently interpretable. This is the approach on which we focused in lectures 4 and 5. A key issue is that very often, machine learning pipelines do not use models that are interpretable, but instead use black box models. To achieve explainability in this situation, a second class of approaches have been developed, approaches which aim to build post-hoc explanations of black box models. Concretely, these models start from a pre-built black box model and then build on top of it an additional explainer model that generates explanations for the predictions and decisions made by the black box. Model-agnostic methods are a subclass of post-hoc explanation methods in which the explainer is independent of the underlying model, and in fact does not have access to model internals, but only to the inputs and the outputs of the model. This is the class of methods on which we will focus in this and the next lecture, the lectures 6 and 7. But before we start going into the details, why use model-agnostic methods? A series of arguments have been put forward. The first argument is model flexibility. A model-agnostic method can in principle be applied on any black box model. This allows model developers to focus on accuracy by developing a black box model and then applying post-hoc explanation methods to it. The second complementary argument is explanation flexibility. Having a range of model-agnostic explanation methods allows to generate different kinds of explanations that meet different needs. The third argument is representational flexibility. Remember that machine learning models take as input data described in terms of a set of features. Representational flexibility refers to the fact that a model-agnostic explanation method can in fact use different features than the original model, and in particular focus on more interpretable features. We will see examples of this. Additional arguments for model-agnostic methods are that having an explainer independent of the model in general leads to a lower cost in switching models. And in principle, it allows to compare explainability of different black box models. Moreover, an important advantage of this type of approach is that, in general, it can be applied to a proprietary black box model and therefore allows to generate explanations without opening the black box. As other interpretability methods, model-agnostic methods can be used to generate 2 types of explanations: local explanations at the level of individual predictions, or global explanations at the level of the whole dataset. As we discussed previously, these 2 types of explanations have different purposes. Local explanations explain individual predictions primarily for the users in terms of specific input features corresponding to them, while global explanations inform experts and developers on the features the model uses with the goal of ensuring trust, reliability, and a lack of bias. Model-agnostic methods typically start by generating local explanations and then aggregate many of them to produce a global picture of the model. In the following lectures, we will review a set of different methods for generating model-agnostic post-hoc explanations. In this lecture, we will cover individual conditional expectations and partial dependence plots, and the local surrogate method, also called LIME, which is one of the central methods of this type. Then, in the next lectures, we will cover three additional methods: Shapley values, a closely related method called SHAP, and finally, a different class of methods used to generate counterfactual explanations. Let's start with individual conditional expectations and partial dependence plots, two very straightforward methods that can be applied to the output of any black box model. Individual conditional expectations, also known as ICE, is a local method. It aims to show the effect of one or possibly two features on the predicted outcome for a given instance. If we focus on a single feature, ICE will produce one line per instance in the dataset. The way ICE works is that we first select an instance I in the dataset. Second, we select a feature S that we want to vary. The output of ICE is then a graph that shows the output of the black box model when varying the selected feature while keeping all other features fixed to the values of the selected instance. Plotting the ICE, we can directly see how the selected feature changes the output. For a simple linear model, this will of course be a linear function. In general, for more complex black box models, the first question is whether the selected instance changes the output monotonically or in more complex ways. Beyond this, the ICE can be used to quantify the importance of varied features in terms of the amount of variation they generate in the output. This is very similar to linear models, where we define feature importance by the coefficient beta of the feature, which is simply the slope of the ICE. Let's look at a specific example, the classical bicycle rental dataset that we already discussed in the lecture on linear regression. The goal here is to predict the number of bicycles rented by a rental company on a given day as function of features such as temperature, humidity, wind speed, and so on. Instead of using linear regression, we can use a more complex black box model, such as a random forest model. This is an example that I'm borrowing from the Interpretable Machine Learning book by Christoph Molnar. For each instance and each feature, we can plot an ICE curve, and this figure shows the result. From left to right, the three panels show the ICE obtained by varying temperature, humidity, and wind speed. In each panel, each curve corresponds to a given instance in the dataset. It is obtained by varying the selected feature while keeping the values of other features fixed to the values of the chosen instance. The first curve shows that the predicted number of bicycle rentals is not a monotonic function of temperature. It first increases steeply, then saturates, and then eventually decreases if the temperature is very high. This effect is very similar across different instances, so it is very homogeneous in the dataset. For humidity, the behavior is simpler, as the output is a monotonically decreasing function. And the same is true for wind speed. Moreover, the amount of variation for wind speed is weaker than for temperature, so that the feature wind speed has a lower feature importance than temperature. As you can see, the amount of variation varies quite strongly across instances for wind speed and humidity, but less so for temperature. This is an example of how ICE can be used to interpret the output of the model. As we saw, ICE is a local method. It produces one curve for each instance, but it can be used to produce a global explanation simply by averaging over instances. The result is what are called partial dependence plots, or PDPs. Partial dependence plots are global methods which show the marginal effects on the predicted outcome obtained by varying one or possibly two features. This marginal effect is obtained by selecting a feature as to vary and then simply averaging over the other features. This is expressed in this formula. PDP generates a function of the selected feature xs, generated by averaging over the values of other features. And in practice, this average can be computed simply by computing an empirical average over instances in the dataset. So altogether, a partial dependence plot is simply an average over individual conditional expectations for different instances. Let's go back to the bicycle rental example and look at partial dependence plots in that case. This figure shows the partial dependence plots obtained by averaging over individual conditional expectations from left to right when varying temperature, humidity, and wind speed. These plots give us a global summary of the effects of these variables over the whole dataset. And you can see here that this global explanation is very meaningful, in particular because the global behavior was largely shared by individual instances. All the ICs were very similar. To summarize these parts on this first set of model-agnostic methods, individual conditional expectations and partial dependence plots are useful because they're simple, intuitive, and very easy to implement. So in general, they provide a good sanity check. It is, however, important to keep in mind that these methods can be used for maximum two features at once, and heterogeneous effects across different instances might be hidden, especially when averaging to obtain a partial dependence plot. Moreover, an underlying assumption is that we need to have access to the original dataset to compute these metrics. We will next turn to a series of more recent specialist methods for post-hoc explanations developed specifically in the emerging field of explainable artificial intelligence. The first method that we'll cover is called the local surrogate, also known as LIME. LIME is an acronym that stands for Local Interpretable Model-Agnostic Explanation. This post-hoc explanation method was developed in 2016 by Ribeiro, Singh, and Gestrin in a research paper entitled Why Should I Trust You? Explaining the predictions of any classifier. And the code for using this method is available on the GitHub of the first author. This figure, taken from the paper, illustrates the goal of LIME. It starts from a black box model that makes predictions based on input data. In this illustration, it takes as input features a set of symptoms and based on them makes a prediction, in this case, flu. LIME builds an explainer model on top of the black box, which produces local explanations for the predictions by assigning a set of feature importance scores to different features. In this case, positive feature importance was assigned to sneezing and headache, and negative to no fatigue. The idea is that a human decision maker then sees the predictions of the model together with a set of feature importance scores, and then can use these explanations to validate the predictions or not. How does LIME work in practice? Let's start going more into the details. The central component of LIME is that it generates a local surrogate of the black box model it aims to explain. What is a local surrogate? It's an interpretable model that is trained to explain individual predictions. How is this done? The key idea is to take the black box model and give it variations of the input data around a specific instance, and then approximate this local input-output transformation by an interpretable model trained on this surrogate data. This interpretable model can then directly be used to produce explanations by using methods that we saw in previous lectures on interpretable models. For example, if we train a sparse logistic regression model, the weights of the different features directly provide feature importance scores, which directly provide explanations for the output. An important aspect of LIME is that the explanation it produces can be formulated as the output of an optimization problem. The output explanation is a function of the analyzed instance x. It is obtained by optimizing a cost function over a class G of interpretable models, such as, for example, sparse linear models. This loss function consists of a sum of two terms. The first term L is a local fidelity or local loss, which quantifies how well the interpretable model G approximates the black box model F around the instance of interest. Very importantly, this local loss depends on a proximity measure πx, which gives weights to different input points as function of their proximity to the instance x being explained. The second term, omega, in the loss is a measure of the complexity of the interpretable model. For example, a measure of sparsity, such as the number of features or the L1 norm as in the lasso optimization for sparse linear models. So this optimization is directly formulated in terms of a trade-off between model prediction or fidelity and model complexity. This is very similar to what we saw for sparse linear regression and sparse logistic regression in the lectures on interpretable models. The final output of this optimization are optimal parameters of the interpretable models, such as the coefficients in the logistic regression, which directly provide a local explanation for the black box model close to the instance of interest x. Importantly, this optimization is done on synthetic data, so it does not require access to the original data used to train the black box model. Concretely, the recipe for implementing LIME can be broken down in a series of steps. The first step is to select an instance of interest. The second step is to perturb the data around that instance and generate black box predictions. The third step is to give weights to the new samples according to their proximity to the instance of interest. The goal here is to really focus on local predictions close to the original instance. The fourth step is to train a weight interpretable model. And finally, this trained interpretable model is used to generate an explanation of the original prediction of the black box model. This is the general LIME pipeline. One important detail to note is that LIME does not specify how to perturb data and how to choose the weights for the generated samples. This is important because in general the results may depend on the choice of the weighting function. To illustrate how LIME works, let's look at a toy example taken from the Interpretable Machine Learning textbook by Christoph Molnar. In this toy example, we are looking at a binary classification problem where the input data consists of two continuous features, x1 and x2. Imagine that we have a black box model, which is a nonlinear classifier. This nonlinear classifier splits the input space into two regions, the gray and the blue region, which corresponds to output 0 and 1. In this toy example, it is easy to visualize this nonlinear classifier, but more generally, this is a black box model and we only have access to the outputs it produces. The goal of LIME is to generate an explanation of how this model produces the output to a specific instance, for example, the instance shown here in yellow. LIME starts by giving a set of randomly generated outputs, shown here as black dots, and then it measures the outputs of the black box model to the surrogate inputs. LIME then assigns weights to the points as functions of their distance to the instance of interest, shown in yellow. LIME in general uses a simple Gaussian kernel of the distance to the explained instance. It then fits a simple linear classifier to the synthetic data set generated by the black box model in response to these inputs. This leads to a linear classifier illustrated here in red. This linear classifier is a local approximation of the full black box model close to the explained instance shown in yellow. In this illustration, this linear classifier is a very good local approximation, but in general, this will depend on how wide the sampling and the weight functions are. This was a simple toy example, but Lime can be applied to almost any dataset and any model by using the code available on the GitHub page. So let's look now at a couple of more complex and more realistic examples. The first example is the classical census income dataset, and this example was taken directly from the Lime GitHub page. For this dataset, the task is to predict whether a person earns more or less than $50,000 per year. This prediction is based on features such as the person's education level, marital status, the amount of gain from capital investment, and so on. So this classification task is based on a mixture of continuous and categorical features. And we start from a situation where a black box model, a gradient-boosted tree, was trained on the task. Then we apply Lime to provide explanations together with the predictions. This figure illustrates the output of Lime for an example input instance. For this instance, the black box model predicts that the income of the person is more than 50K with very high probability. This is shown on the left. Lime then gives us an explanation in terms of a list of features classified by their contribution to the output. This is shown in the middle. For each feature, the length of the bar is its contribution strength or feature importance. Lime tells us that in this case, the largest contribution was due to the fact that the person had high capital gain. The second largest contribution was marital status, followed by education level, the number of hours worked by week, and finally, age. The table on the right gives us the values of the corresponding features. This was one basic example for tabular data. The strength of Lime is that it can be applied to other kinds of data, for example, text. Here is an example of application of Lime on text data, the IMDb dataset, which consists of a set of movie reviews, and the goal is to predict whether the review was positive or negative. This is a classification task called a sentiment analysis task. We can train a black box model, such as a random forest, to make this classification. And then we can use Lime to produce explanations for the outputs of this black box model. In this case, Lime is applied on text data, and it builds local surrogate models by perturbing individual words based on a bag of words representation. Here is an example of the output of Lime for one example instance. On the left, we see the output of the black box model, which predicts that the review is negative with high probability. On the right, we see the output of Lime, which gives words in the review with the highest contribution to the output. In this case, Lime tells us that the review was negative because it contains the words worst, waste, bad, and awful. As a final example, Lime can even be applied to image classification. Here, a deep neural network is trained to classify images, so for every input image, the network outputs a set of labels classified by relevance. Then Lime can be used to produce explanations for each label, and it does so by perturbing superpixels. What are superpixels? They're sets of interconnected pixels with similar colors. Lime replaces them by a user-defined color and then checks how switching them on and off modifies the output for each of the top labels. For example, for this input image, the three top labels in the network output are electric guitar, acoustic guitar, and Labrador. Then, by perturbing superpixels, Lime basically identifies regions of the image that contributed the most to each of the labels. To summarize, Lime is a method for generating post hoc explanations that has a number of advantages. It can be applied to a large set of black box models. It inherits techniques for training and interpreting interpretable models. It can be used with different types of data, tabular data, text, or images, and it does not require access to the full training dataset. The main disadvantage of LIME is that it does not provide a principal choice of neighborhood in which the inputs are perturbed, and this sometimes leads to issues with stability. This brings me to the end of this first lecture on model-agnostic post-hoc explanation methods. In this lecture, we've discussed three explanation methods: individual conditional expectations, partial dependent plots, and LIME. In the next lecture, we will continue with three other methods: Shapley values, SHAP, and counterfactuals. Stay tuned and see you soon.